Thanks for Chair's introduction. Okay. Thanks for Chair's introduction. My name is Cheng Zhenzhou. I am a professor in the School of Precision Instrument and Optoelectronics Engineering, Tianjin University. I feel very honored to have this opportunity to share my research progress in the medium-infrared silicon photonics and Optica event seminar, Optica seminar event at Tokyo. So today's my presentation is a foundry-processed silicon photonics for short wavelength mid-infrared. Okay, sorry. Okay, sorry. Okay, so this is the outline of my presentation. First, let me briefly introduce Tianjin University. Maybe some of the audience not very familiar with this university. Then I will talk about the motivation of our study. And then I will discuss the light coupling technique between the optical fiber and the silicon waveguide in the short wavelength mid-infrared. And then I will briefly introduce photonic bandgap device we are working on recently. Is a hyper-uniform disorder solids. Finally, I will summarize my talk at the end of this presentation. So this is the picture of Tianjin city. So it is my hometown. And Tianjin is the industry and economic center, one of industry and economic centers in China. Is very close to Beijing. So the distance between the Tianjin and Tokyo is 2,020 kilometers. I Googled it yesterday. And with the airplane, it takes around 3 hours. I think there are many Tianjin elements in Japan. So this is a very famous snack in Japan, I think. It's the Tianjin amagori, right, in Japanese. So to be honest, I didn't know this is the Tianjin special snake until I arrived in Japan. So, but anyway, I think maybe many people in Japan see the Tianjin in their daily life. And Tianjin University is the best university in Tianjin city and one of the best universities in China. So she is the oldest institute for higher education in the modern history of China. And she was established in 1985, sorry. And she has 127 years old. Previously, her original name is the Beiyang Daxue, Beiyang University, and then changing its name to Tianjin University in 1960s. Yeah, then now we have two campus. One is the main campus, and the other is campus in downtown. Yeah, I joined Tianjin University in 2019. Previously, I was an assistant professor at Tokyo. I joined the Goda Lab in Department of Chemistry in 2016. Then I go back to Tianjin University as a professor. So when I worked at the Tokyo, I always visit Yamashita and SET lab, and Yamashita Sensei and SET Sensei provide me a very good support to my research. So, you know, due to the COVID-19 problem, so I have not been to Japan in the past 3 years. I think maybe in the future we can visit each other, maybe in the next year, because the quarantine policy in China is changing. Yeah, so let's go back to today's presentation. So in this presentation, we are working on the short wavelength mid-infrared in the wavelengths from 2 micrometer to 2.5 micrometer. So in this wavelength range, this is the 1 atmosphere transparent window. That means the air can transmit in the light can transmit in the air with very low loss. And also the photon energy in this spectral range correspond to the fundamental vibrational transition of some gas molecules. So we can use the absorption spectroscopy to do the gas sensing. So there are many applications in communications, in radar, and in sensing and spectroscopy. Here I list some examples. One is a 2 micrometer optical communications. This is I think an emerging topic and very promising topic in the optical communications to expand the spectral bandwidth of communication system. So now there are commercially available low loss fiber and fiber amplifiers for 2 micrometer wavelengths, and the development of the optoelectronic device for the 2 micrometer optical communication is also very quick. And another application maybe is remote sensing. So 2.08 to 2.35 micrometer is the Landsat TM7 band of the remote sensing satellite of the United States. You can use this wavelength to monitor the river and the rock on the surface of the air. And also there are many greenhouse gas has strong absorption in this region, and such as carbon dioxide, methane, and we can use the spectroscopy to do the environmental monitoring. Yeah, so this is the application of the short wavelength medium infrared from the wavelengths from 2 to 2.5 micrometer wavelengths. Yeah, what we are starting is to develop the optoelectronic device and system on the chip. So actually there are many platforms can be used in the short wavelength medium infrared. We mainly focus on silicon photonics. Silicon photonics is study and application of photonics device and system, which use silicon as optical medium. In silicon photonics, usually we start from an SOI wafer, as shown here. The device are fabricated on the top layer silicon. It's very thin, just 100 nanometer thick. And below the top layer silicon, there's silicon dioxide. Due to the refract index contrast, the light can be well confined on the top layer silicon. We also use the CMOS technology to fabricate the device on the top layer silicon and to fabricate some waveguide like this. So previously or conventionally, the silicon photonics is designed target to the communication band, the wavelengths around 1.55 and 1.3. But our work is to explore the possibility to extend the silicon photonics to the short wavelength range by using the Foundry-Processed. I will go to some details in the following slides. And the silicon has a very wide transparent window, as shown here. This figure is published by Professor Sarif in Nature Photonics 2010. The light color region is the transparent window of different materials. As for silicon, it's transparent from 1 micrometer to 8 micrometer. And the silicon dioxide is from visible light. And here he marked as 3.5, but actually in 2.6 or 2.7, the silicon dioxide have very strong absorption here. Yeah, so silicon and silicon dioxide are commonly used materials in CMOS compatible technology. So in CMOS technology, so if you want to use the standard, the CMOS process to fabricate a photonic device, so you have to ensure that the material transparency in this region. Fortunately, from 2 to 2.5, and in this region, both silicon and silicon dioxide are transparent. And if you want to explore the long wavelength range, for example, in 3 to 5 or 3 to 8, you can use the silicon. And if you want to explore the long wavelength to around 10 micrometer or even 12 micrometer, so you have to use another CMOS compatible materials such as germanium. But the silicon dioxide has very strong absorption in this range. In my previous study at U Tokyo, I developed some germanium photonic integrated circuit for long wavelength medium FRAD. As I have mentioned, the germanium has a very wide transparency window, even up to the wavelength of the 12 to the 15. So we collaborate. So we fabricate the suspended membrane structure by using the hydrofluoric acid to locally remove the silicon dioxide below the germanium waveguide and make the device suspend in the air. And the device, this is the waveguide, and the waveguide can be supported by the two-side cantilevers. And we also fabricate the photonic crystal structure and the microring resonator. Some of this work is collaborated with Yamashita and the SET lab. And yeah, so this is my previous work. And then this is can provide us a very good platform to explore the long wavelength medium FRAD. But as for the short medium FRAD wavelength, we don't need to remove the silicon dioxide. As I have mentioned, the silicon dioxide has good transparency in this region, such that we can using standard the commercially available the foundry process to fabricate the silicon device. So based on this process, it is maybe possible to fabricate a high density integration photonic system on the chip, because the foundry process not only provide us state-of-the-art performance, but also very high reproducibility of device fabrication reproducibility. So this is the transparency window of this is the optical absorption of silicon and the silicon dioxide materials. The blue color is the two-photon absorption coefficient of silicon. And we can see in the wavelength below 2 micrometer, the silicon has a very strong two-photon absorption. So this is the main limitation when we started the silicon photonic device in the telecommunication band, especially for the high power application, such as a nonlinear study or the high power LiDAR, something like this, because the free two-photon absorption effect will transform the electron from the valence band to the conduction band and make the electron become the free carrier in the waveguide. And this free carrier absorption could generate a huge loss to the propagation light in the waveguide. So, but when the wavelengths beyond 2 micrometer or even beyond 2.2 micrometer, the two-photon absorption coefficient became negligible. So I think this is one advantage of the silicon device in the short infrared mid-IR. And well, on the other hand, if the wavelength is very long, for example, larger than 2.5 or 2.6, the silica has very strong absorption to the light. So the red dashed line is the silica absorption coefficient. Although the most of the power, most of the energy is confined into silicon waveguide, but some of them will leak into the silica substrate or cladding through the evanescent field. So it is necessary to reduce the wavelength to reduce the absorption from the silica. So this is the reason we choose the wavelength from 2 micrometer to 2.5 micrometer to give the device the very low nonlinear loss in silicon and the low linear loss from the silica. So I think this is the advantage of using the silicon device in the short wavelength mid-IR. Yeah, and then I will briefly introduce what is the MPW service. The MPW is the standard fabrication process of the silicon photonic foundry. They fabricate the silicon device on a wafer by using standard process, and then they divide the wafer to the small chip, small die, and the different users can share with one wafer, so it can let the user use the reasonable cost to design their device. And also this process is can give us a very good reproducibility. So this is the cross section of the waveguide, shows the most standard fabrication process of our MPW service. For example, this is the thickness. This is the SOI waveguide, as I have mentioned. The top layer, the thickness of top layer silicon is 220 nanometer, and they provided 3 etching steps. One is the go through 220 nanometer. Another is the 70 nanometer, and also is a 150 nanometer. And below the top layer silicon is the boron oxide. The thickness of the oxide is 2 micrometer, and the feature size of the design is 180 nanometer. So this is a limit by the photolithography that using the UV light. So after you fabricate the passive device, you can do the ion implantation to fabricate the PN junction and deposit germanium or heater or something like this. Yeah, so this process actually optimized according to the telecommutation band. So why they choose the different wavelength, different etching steps, just 70 nanometer or 150 nanometer, or rather other etching steps. I will introduce in the following slide. So basically, this is the optimized target to the 1.55 micrometer. So our study is to see, can we develop the high performance photonic device based on this standard process for the short wavelength mid-infrared. So this is what we are starting in the first step. Yeah. So the first difficulty is light coupling. So from the optical fiber to the silicon waveguide. So if you are not very familiar with silicon photonics, you may think this is a very trivial problem. But in practical, it's a non-trivial problem because the mode has the large mode mismatch between the optical fiber and the silicon waveguide. So this is the cross section, the schematic of cross section of a fiber, and the diameter of the core is about 10 micrometer, and the diameter of the mole field is around 11, more or less. And as for the silicon waveguide, here we can see the width of the waveguide is maybe 500 to 1 micrometer, and the thickness is just 220 nanometer. So a very tiny area. So if we couple the two types of waveguide together, there's very large mode mismatch and limits the coupling efficiency less than 100%. So in this case, we have to develop some device to improve the coupling efficiency from an optical fiber to the silicon waveguide. The device we used is the grating coupler, as shown here. This is a fiber, this is a silicon chip, and we can couple the light through the surface of the chip, so by using the grating coupler. So here we're using the standard the fabrication process in the silicon foundry. So as I have mentioned, all the fabrication process has been optimized according to the 1.55 micrometer. So the coupling efficiency of the grating coupler is reasonable good. The peak coupling efficiency is around 40%. This is the external result and provide us quite good reproducibility. But if we go to the short wavelength mid-infrared, the coupling efficiency is the moderate. Here, we calculate the directionality of the grating coupler. So what is the directionality? Here, I put the schematic of the grating. So the light is coupled from the silicon waveguide and then face the grating coupler. After the light go to the grating coupler, the light can be diffract on the upside and the downside. And the percentage of the power to the upside is defined as the directionality. So that means we want to, ideally, we want the directionality to be 100%, you know. We want all the power. The grating coupler can couple the 100 power from the silicon waveguide to the outside. But in practical, it's very challenging. You can see if this directionality depends on the etching depth. If we only have two etching depths, for example, 70 nanometer and 150 nanometer, and the directionality is lower than 30%. That means only 30% light in the waveguide can be coupled out of the chip. This is not the coupling efficiency. You know, you cannot collect all the coupled power into the fiber. So there's also another mismatch between the diffracted light and the optical mode in the fiber. So only maybe 70% or even 60% light can be collected by using the fiber. So if we consider the mode mismatch between the diffract power and optical fiber, so the real coupling efficiency should be around 10%, more or less, by using the standard fabrication process at the center wavelength of 2.35. So this is one challenging we faced when we using the foundry process, the silicon photonics foundry process, to develop the short wavelength mid-infrared photonic device. So the method we used to overcome this problem is using sub-wavelength grating. So maybe some of you are not very familiar with this. I will give a very brief introduction. So when the light incident to a periodic structure and the light, what will happen? You know, what will happen? So it depends on the period and the incident light wavelength. If the wavelength is very small, that means the energy is large, but high frequency for a given periodic structure, it became the radiation mode as shown here. So if you're using the longer wavelength, so it's go to the Bragg grating, Bragg refraction region, and the light incident light into the periodic structure, and the energy feedback, reflection back. And if we filter increasing the wavelength of the light, and that means the shorter the frequency, and it go to the sub-wavelength region. That means the light can propagate into the periodic structure. So to the light, this periodic structure is like a homogeneous structure, like a homogeneous waveguide. So if in short, if we using a very long wavelength to incident a periodic structure, compared with the period, here the long is compared to the period, the light could be propagated into the periodic structure, as the periodic structure is like a homogeneous medium to the light. So we use this concept to the grating coupler design. So the grating is the refractive index periodic change material device. Here we defined a two-dimensional grating That means we fabricate a lot of holes on the grating coupler. In the lateral direction, in the X direction, we reduce the period of the grating. And that means we make the light work in the sub-wavelength medium. So in the lateral direction, X direction, it seems like a homogeneous medium to the light. So the refract index of this medium can be calculated by using the effective medium theory. Here, I didn't show any formula to disturb you. So this formula is very boring, you know. So I just give the result. So if you, for example, this is the x-axis is the lateral field factor, and the y-axis is the refract index, effective refract index of sub-wavelength medium. So if we the field factor is very high, that means all the holes connect together. So all the areas is the air. So the effective index of this medium is 1. It's the same with air, right? On the other hand, if the field factor is 0, that means there's no hole. So the effective medium, the effective refract index of the medium is the same with the silicon as 3.47 more or less, as shown here. And then between them, we can using the field factor in the X direction to change the, you know, to engineer the refract index of sub-wavelength medium. So in that case, we can construct a refract index periodic change. We can construct a grating with the refract index periodically changed in the Y direction. So this is the concept of sub-wavelength grating. So why the sub-wavelength grating can changing the directionality of the grating coupler? So as shown here, the light is coupled from silicon waveguide and then face to the grating coupler, and this etching depth will influence the diffraction direction. You know, so if we because we use the Foundry-Processed, so the etching step is fixed. We only have 3 etching steps: 70 nanometer, 150 nanometer, and 220 nanometer. So, and all this etching depth is optimized, you know, with respect to the telecommunication band. So in the short wavelength mid-IR, so the directionality is very poor. But if we using the sub-wavelength structure, so this is similar like, you know, the symmetric. If we using the silica as a cladding, when the light is coupled into the sub-wavelength grating, theoretically, 25% light will coupled out into upward, and the 25% light will coupled to the downside, because this is a symmetric structure. So this is why we can using the sub-wavelength grating structure to improve the directionality of the grating coupler. So we calculate the directionality and compare with the shallowly etched grating coupler. The sub-wavelength grating can improve the directionality to more than the 50%. Yeah, so we fabricate this device based on IMPW service, Silicon Photonics Foundry. And this kind of foundry are widely accessible. There are many places have this kind of foundry in Japan, in Singapore, and in China, in the United States, and many companies can provide such service. So this is a grating, and this is a waveguide. This is another grating, and we using one fiber to couple light from one grating coupler, and using another fiber to collect the diffracted light and to test the transmission of the device. So this is our experiment result. The result shows that we can achieve a 20% couple efficiency per grating with a 3 dB spectral bandwidth of around 90%. So you can see the silicon photonic foundry fabrication can provide us very good reproducibility. We got almost the same testing result on the different die, and also we can change the the center wavelength of the grating by gradually reduce or increase the hole size, and we change the center wavelength from 2.35 to 2.42. Yeah, we can flexible change the center wavelength. So this is our very preliminary result to fabricate the subwavelength grating in the short wavelength medium infrared region, and give us a very good reproducibility and reasonably coupled efficiency. Also, but the problem is the coupled efficiency is still moderate, and we have see a lot of ripples in the coupling profile. So this ripples came from the fiber Pro effect in our device, as shown here. When the light coupled into the grating coupler, some energy will reflect back due to the refractive index contrast between the grating region and the slab region. So some energy reflect back and face the other grating coupler, and then they reflect forward and back and forward. This is like the fiber Pro cavity. So this fiber Pro cavity result this fraction ripples in coupling profile. So how to solve these two problems? One is the high back refraction, another is the moderate the coupling efficiency. So we also propose a new design. It is an hybridized blazed sub-wavelength grating coupler to further improve the coupling efficiency. So this is the schematic of the grating, and this is a cross-section view, and this is the top view. When the light is incident from the silicon waveguide to the grating, in our previous result, we just used one single etching steps. So to construct the grating as shown here, single etching steps. Here, the etching through to the bottom of the burn oxide to the burn oxide. Here, we using the 3 etching steps. Do you remember I have mentioned in the foundry process, it can provide us 3 etching steps. One is the etching through to the burn oxide. Another is etched to the 150 nanometer, and then is the 70 nanometer. So we're using the 3-step etching to construct a blaze grating to improve the directionality to the fiber, to couple to the fiber. So this is the blade structure, 3 steps grating. Another technique we use is the hybridized grating. We carefully engineered we don't use the uniform the grating period. We carefully engineered each grating period and the fill factor in the X direction to make tailoring the coupling strain. In the beginning of the grating, the coupling strain is weak. In the middle of the grating, and the coupling strain is strong. And then in the end of this grating, the power is weak. So the coupled power is a Gaussian shape. So it can match well with the mode profile in optical fiber. In other words, the fiber can efficiently collect the power from the diffract light. So this is our simulation result. The above one is the uniform blaze subwavelength grating, and below one is the hybridized blaze subwavelength grating. Both of this design, we use the blazed structure. So the directionality is calculated as the more than 80%. That is means the more than 80% energy can be diffracted out of the chip. in the hybrid structure, we carefully engineered each grating period to make the diffract light a Gaussian shape. So the mode overlap factor between the diffract light and the Gaussian and the mode profile in the fiber is 90%. If we using the uniform the structure, that is means we use the same period and the fill factor in the x direction, the overlap factor is just 75%. So we can do the very simple math. 80% multiplies 90%, the couple efficiency should be 70%, right? Yeah, so this is our simulation result. We can see by using the hybridized subordinate grating coupler, the couple efficiency is around 70%. But if we could increase the thickness of top layer silicon, not 220%, 220 nanometer, if we using 340 nanometer wafer, SOI wafer, increase the thickness of top layer silicon, and the coupling efficiency can be further improved more than 80%. So this is the theoretical result by using the 2D simulation. So we fabricate this device with the same MPW foundry as shown here. This is the hybridized blaze subordinate grating. If we zoom in the grating period, this is the real device we fabricate. It's not the same with our design. The original line, the original dash line is our design. We can see the fabricated device is not the rectangular shape. This is because the fabrication error. And this is the etching depth of 220 nanometer. And this region is the etching depth of 150 nanometer. And this etching depth of 70 nanometer. And but fortunately, this design is very robust. Although the structure is almost totally different with our design, it still works well. So this is our experiment result. And the red line is the measurement. We have demonstrated almost 4.53 dB per grating coupling efficiency with a 3 dB bandwidth of 100 nanometer, and also can provide us very good reproducibility as we have done previously. We can changing the center wavelength of the grating by gradually reduce the hole size or increase the hole size. The maximum coupling efficiency is more than 35%. It's almost slightly lower than the result in the technical compression band in the standard fabrication foundry. Besides this, we also try some other device based on the MPW service. Here I will introduce another one. It's ultra thin grating coupler, ultra thin silicon waveguide. So the typical silicon waveguide fabricated by using foundry is 222 nanometer thick. So most of the energy is confined to the waveguide, and just a very small part is around the waveguide. So the evanescent field, can interact with the environment to do the sensing. So the advantage of this structure is a very low optical loss, but maybe it's not very suitable for the sensing, because we also interested in we developed a short infrared mid-IR device for some applications in sensing. So we think about how can we fabricate the ultra thin waveguide, the 20s, just tenths of nanometer thickness, and as shown here. So most of the energy could be leak out to the environment and interact with the environment gas, something like this, and it can provide us the GEN, the optical evanescent field, and a very large optical modes. So we fabricate this device based on the foundry. as shown here. Because as I mentioned many times, it is the standard foundry process. They only can provide us 3 etching depths. So one is the 220 nanometer, and then it's 115, and finally it's 70 nanometer. So we're using the 150 nanometer to etching the whole structure and make the thinner the top layer silicon. So there's only 70 nanometer top layer silicon left. And on this left structure, on this left top layer silicon, we define some structure to fabricate the waveguide and the grating. This is the SEM image. You can see this region is etched by the 150 nanometer process, and then based on this very thin top layer silicon, we define the grating coupler and the waveguide. In this work, we're using the HF solution to remove the silicon dioxide below the top layer silicon device, and make the device suspend in the air, such that this could be possible to work for sensing. Yeah, so this is our experiment result, and we have demonstrated about 20% coupling efficiency for grating. It's not very good, but surprisingly, the coupling profile is quite smooth. As you can see, there's almost no the fragile or the ripples in the coupling profile. That means the back refraction of the grating coupler is very low. And but the coupling the efficiencies are just only 20%. We do some calculations, 3D FDD simulation, and find that if according to our design, the 70 nanometer thick the grating coupler can provide around 4 dB coupling efficiency per grating, but actually we only achieve 7 dB per grating. So the reason we think it's due to the variation of top layer silicon. The real top layer silicon is not 70 nanometer thick; it's just 50 nanometer thick. So it has reduced the coupling efficiency. You can see the experiment result agrees well with the 3D simulation of the first 50 nanometer top layer silicon. Yeah, so the reason is the reduction of top layer silicon layer, reduction of the top silicon layer. Yeah, so we also measure the loss of this waveguide. So you may wonder how does it can guide light or the very high optical loss? Yes, and we have measured the different bands, and according to our experiment result, per 90-degree band, it can introduce the 0.31 dB loss from the waveguide, ultra thin waveguide. So this may came from the surface roughness, because we're using etching, the DRIE etching to reduce the surface. So I think the top layer surface should be very lossy. If we can have some annealing process or using the chemical mechanical polishing to reduce top layer silicon, we think that the loss could be future reduced. So yeah, so this is another work we started in the short infrared mid-IR based on the silicon photonics foundry. So in this figure, I summarized our result and the previous work of the grating couplers in the short wavelength medium infrared region. So now we have achieved the widest bandwidth and the highest coupling efficiency theoretically, and the almost highest coupling efficiency experimentally. So in the future, I think we need to think about a new design on new process, maybe to future improve the coupling efficiency, to improve the performance in this direction. The final goal is we want to achieve the high coupling efficiency and the larger bandwidth. I think the time is almost. I just want to use very quick to introduce another project in my team. To in this project, I would like to collaborate with the Yamashita sensei and Seth sensei in the future. So this is the hyperuniform disorder solid. It is kind of the photonics bandgap structure. It's proposed and demonstrated by Professor Steinhardt at Princeton University. It is the kind of the distribution of the point can provide us very hyperuniformity, and based on this point, the photonic device could provide this larger bandgap, and it's isotropic. The bandgap is isotropic. So the uniformity of the distribution can be defined by using the formula I didn't show here. This is we can use the degree of hyperuniform to describe how uniform or how disorder of this point distribution. As shown here, this distribution has very small degree of hyperuniform. The chi is very small, and we can obviously this is not uniform, but if we are changing the distribution of the point and makes them more uniform, it became the hyperuniform. This have the distribution with a very large chi. Based on this distribution, we can fabricate some structure on the silicon waveguide, and then we simulated the bandgap of this structure. It shows us very good the isotropic. This is not like the conventional photonic crystal. The bandgap is different with different direction. Here, we define the different direction, and the bandgaps are almost uniform and isotropic. And we fabricate this device and make the defect as a silicon waveguide, and using the grating coupler to couple the light from the hyperuniform waveguide, and testing the light transmission and test the waveguide transmission. So this is our simulation result, the black dashed line, and red line is the experiment result. We have observed the photonics edge in this device. So in the future, I would like to, based on this platform, to explore some the nonlinear study, the slow light effect in this structure. Yeah, I think time is up. Finally, I would like to summarize my talk. In this presentation, I have presented our efforts of developing the grating coupler and ultra-thin waveguide and the photonic bandgap device in 2 to 2.5 micrometer wavelengths based on silicon photonics foundry service. And this work is partially supported by the National Nature Science Foundation and the Nature Science Foundation of Guangdong Province. Yeah, thank you very much. And the questions are welcome.
Thank you very much, Dr. Cheng. I would really like your slides. I noticed there's so much fantastic structures, pictures in your slides. Yes, thank you very much for your presentation. Now, I would like to call the Q&A section. So if any audience have questions or comments, just unmute yourself and speaking, please.
I forgot to open the video, sorry. Hello, Sensei.
Hello.
Hello.
Hey, good to see you. I'm sorry we did not manage. I would like to talk to you after this later on, okay, in more detail. Okay. I have questions. It's very nice talk you have. I have a question about just a thought, right? The grading design you've done, I think is amazing that you're using this sub-wavelength features. I just start with a simple question. So the sub-wavelength feature has to be at least 10 times smaller than the wavelength, or is it 20 times? Is it a guideline how small you need to be before it become a sub-wavelength feature?
Okay, thanks for your question. Actually, it don't need to 10 times or 20 times smaller than the wavelength. For example, in our design, and if the wavelength, the requirement is the period should be less than the light propagate into the waveguide. Okay. For example, if you do very simple calculation as for the 2 micrometer wavelength, and the effective index of the waveguide, for example, is a 2. So the wavelength in the waveguide is 1 micrometer. And so if the period is smaller than the 1 micrometer, so it can be seems like sub-wavelength. Actually, the effective media area can works well if you design the structure smaller than the 1 micro. The period is smaller than the 1 micrometer. Of course, if you're using smaller structure, it give you a better result, I think. Yeah.
All right. I was assuming that it had to be like the period has to be 10 times smaller. Otherwise, you may get more, maybe ripple or something else. Okay, yeah. So it's just to be a little bit lower, not that much, and it's within your lithography ability, right now, because you of course your foundry lithography line width is that like 70 nanometer.
The feature size is the feature size is 180
okay
nanometer.
All right. Oh yes, 180, and that is good enough, right? Okay, great. And I also have to have a comment, a thought about the thing that you use to reduce the ripple. Is very, very similar in concept with fiber break grading design, which Yamasa Sensei and myself have worked a lot. All this idea about apodization and a few ideas. I'm just wondering if there's any way that you could even make more advanced feature. Now you've gone through Blaze and you have gone through apodization. Is it any chance in the future to go through some design that gives you, in theory, a flat top spectral response will involve your grating design to apodize in a sync shape, and the negative index will be done by, of course, the 180 phase shift, right? 90-degree phase shift of your grating. So is it possible to do some really advanced phase shifted as well, kind of grading design structure to, for example, make your acceptance spectral response flat top? I'm not sure. That could be, in theory, kind of interesting to me.
Yes, I think it's maybe possible. Yeah, we need to do more calculation and design. Basically, the physics in silicon photonics and the fiber is the same, because then we just change the platform to design the device. And I think the answer is possible, but we need to try. And yeah.
But I'm not sure if there's any merits to make the acceptance spectral feature characteristic flat, because making it flat would also means that you most likely will lose the efficiency.
Yeah.
Okay.
You are right. Sometimes with the bandwidth, you sacrifice the efficiency.
All right. Very interesting. And another thing that you talk about making these highly uniform structures. Those are some sort of patterning that you design, right? I guess so. Is that pattern kind of random? Or you have a design structures that you have to follow?
Yeah, the beginning distribution is kind of random. You can and in the Poisson distribution of this point, and then you can optimize the distribution of this point by using algorithm. So simply speaking, you need to fix a sampling window, and then you can count the point in the sampling window, and then you slightly increase the sampling window, and when the increase of the point increase the bit of the point in the window is lower than the increased area of the sampling.
All right. All right.
I am clear, and this make the distribution kind of the hyper uniform, and then in that case, after you get the I'll say the hyper uniform the distribution, you connect this point and make the structure like this way, and you put this structure to the FDDT and set some dipole to testing the photonic band gap in different direction, and you can render the the band gap here. Yes, that means because we set some direction. This direction is the we set by ourselves. It's not the same with the conventionally photonic crystal direction, because this is random, like the random. When we set this is a gamma, this is a M, for example, and this is a R, and you can see in each direction there is a band gap. It's not very different the conventional photonic crystal device. Yeah, and
that's amazing.
Yeah, after that we make a line, make a define, filling some region like the waveguide, and testing the transmission can give us for me it's like a band gap, band edge here, because the transmission suddenly decreased here. Yeah,
that's right. Amazing. You can engineer that, and possibly they will also have dispersion that you could design into the waveguides. Yeah. These are all done by Foundry service as well, right? You send it out. That's really amazing. They could do that now.
Is that material the silicon?
Yeah, silicon. Okay. Yeah. So we do this. To be honest, we do this experiment. We do this. We carry out this kind of research because we want to rely on a standard foundry to fabricate some good performance device with very high reproducibility. So we intently try to find some structure which may provide us a very good reproducibility. The random, the bad thing is the random, and good thing is maybe very high reproducibility. So we chose this rather than the conventional photonic crystal device. Yeah.
So you basically etch through, right? For this pattern, you etch all the way through, right? You did not do any layering. Yeah. Okay. Yeah. Very nice. Very nice. We have read the paper, Yamasa Sensei and myself. We like to have another meeting later. I thought it's very interesting proposal that we also have some idea we want to tell you about, what we are also interested to try out with your platform. You did mention that the foundry could do ion implantation, right?
Yes.
Only P and N doping, right? So that would drastically, I believe, will increase the nonlinear efficiency coefficient of the waveguide as well when we do ion implantation, right? It could be something that we are very interested in to take the nonlinear, especially the Kerr effect of the waveguide, to do something interesting there. All right, great. Is that foundry in China or in Europe or
in China?
All right, that's amazing. That's cool. That's cool. Things will be so fast. Yeah.
What about the lead time? I mean the time for the complete the devices.
Okay, you mean the delivery time? Yes. You set mask and you get the device. That's maybe 3 to 4 months.
Okay, that's not too bad. It's very standard. 3 to 4 months is
previously 3 to 4 months. Yeah.
All right.
So to be honest, after leaving the Tokyo, I cannot find a very good fabrication facilities in China. So I try a lot of places and just can publish some simulation work. And finally, I go to the foundry and to using standard process to fabricate the photonic device, and just to think about the new design rather than pay more attention down to the fabrication process.
I think it's very nice, very smart. I mean, this is the way to go, right? You want something that you could, if high repeatability, reproducibility, and that had more meaning in terms of engineering research, because then you could then deploy it, right? Rather than you can make one perfect device, only you can make it, you can publish into nature, but it's never going to see the lights to application. So I think you're going to the very, very nice direction right now. I really looking forward to. I think it's great. Yeah.
Thank you. Like this structure, you can see the fabricated structure is not like our design. But if we talk to using the lithography, it can the design should be the similar. The fabricated device should be very similar.
All right, the error is higher, right? Okay. You mentioned that you cannot get 70 nanometer. The design was 70, but it actually gave you possibly 50 nanometer thickness, right? For the thin. Your thin clad. Okay.
Yes. So it is the variation, the etching process. But the good thing is the foundry process very, very, very stable. Yeah. If you have this result this time, maybe next time you have get almost the same result.
Same result, right?
Yeah.
They are mostly doing electronic devices foundry, or you're just applying. I guess the foundry, they are not really specialized in silicon photonics, right? They are doing in generic foundry services. Like
actually, they can provide a lot of service. We use a silicon foundry part, silicon foundry model, a silicon photonics model. Yeah.
They have a kind of design package that I know.
Yeah, of course.
They'll give it to you, right? So you okay? All right.
Yeah.
That's really nice. That's amazing. Thank you so much. Now, do we have questions from? I'll leave time for other attendees to ask questions.
So Cheng says, so thank you very much for the very interesting talk. And congratulations on your very good results. And so when you say about the coupling efficiency, is that the efficiency from the silicon photonics waveguide to the optical fiber?
Yes. Prorating, yes, just because for example, here the result is, for example, is 25% is from the waveguide to fiber per grating coupler. If you count 2 grating, because it's one input and then other output, the totally transmission should be the 10% around.
Is that this silica fiber?
Silica, yes, because in this region the silica has a very high transparency. If we use if we start the wavelengths beyond 2.5 or even 2.6, we need to using the Zebra fiber. So
coupling to the single mode fiber.
The single mode fiber, yeah.
That's very nice.
One quick question. When follow up with the fiber coupling, are you using a lens fiber or it's just a clip fiber to couple?
A clip fiber, not
a very simple clip fiber, right?
Yes.
Okay, that is very nice. But then your clip fiber will have back reflections, right?
Yes.
So would that be contributing to your ripple?
We didn't account this in our the coupling efficiency measurement. Yes, you are right. It have some percent, maybe 3% back.
Close to 4%, right? So you may want to in the future, if you do AR coat, it's going to be difficult. AR coated fiber or angle cleave. I'm not sure, but
yes, you're right. If you be using the cleaved angle or using the lens fiber, the coupling efficiency should be also improved a little, I think. Yeah.
All right. So I'll get back to Bowen, the chair. So Bowen, would you like to take over and ask if there's more questions?
Yes, thank you, CC. I would like to recall for the Q&A questions. Is there any other comments or questions? That's please unmute yourself.
Hello, Professor Cheng.
Hello.
Can you hear me? Yeah, thank you for your presentation. It's very interesting and nice. I have some very simple question. Maybe based page 13. 13.
13.
Yeah, it's about the. Yeah, I noticed the arrangement of the holes is it's like a circular arc shape. So
Yeah.
I want to know what is the difference between you just arrange it in a line or like this shape? Is there any reason for this? Is advantages?
Okay. So
Yeah.
this is kind of the focus grating. So
Yeah.
in 2D FTTT, we designed the grating coupler like this way. And then we using a formula to slightly curve this how to say the straight line to this the circular line. And the advantage of this kind of grating, it can reduce. They almost don't need any tapers between the grating to the waveguide. So the total area here you can see just 20 micrometer length.
Yes.
And if you're using this kind of the grating coupler, you need a taper from the grating region to the waveguide region. And usually the length of the taper should be larger than maybe 100 or 200 micrometer. So by using the focus structure, you can greatly reduce the device footprint. Yeah.
Okay.
So this is main reason, the main advantages of this device.
Okay, that's good. And I also have a simple question about maybe page 15, about the blade structure. Yeah, this page. Yeah, I think it's very good to choose this structure, but I noticed that it's also the 3 depths, right? The 70 and 50, 150 and 220. So I wonder, is there any possibility to choose maybe the other combinations that can make better collect efficiency? And
yes,
yeah,
of course. Yes, of course. So yeah, of course, if you because in our fabrication, we all the design and the fabricate is based on standard foundry. They just provide us 3 etching depths, as I mentioned here. Yeah. So if
it's limited by this condition. Okay.
If you have your own process, you can well control the fabrication condition, and you can ideally the blade grating is an angle like this continually change.
Okay.
A very much better result. But in practical, it's very challenging to fabricate this continually change the
okay, I see. Okay, thank you very much.
Yeah, thank you for your question.
Okay, considering the time is a little bit over, I would like to have one more question left. So if you have any question, comments, it's the last chance. Okay, it seems there's no any questions or comments left. So let's thank for Dr. Cheng for this vivid presentation again. Thank you very much, Professor Cheng.
Thank you. Yeah, thank you, Amashita Sensei. Thanks, Bowen. Thank you. Thank you.
And please, everyone, don't forget to click on the chat box. This is a survey form. We do that every seminar. Please take some time to check a few boxes in the survey form. And Professor Cheng, will you come to my other room for a quick chat? I would invite. I've sent you the number.
Okay, I have received number.
Yeah, I would open that room in a minute after we close this, but I think we're closing that now, right? Okay. So everyone, don't forget to put in your feedback. Thank you so much for attending. We are very pleased to have Professor Cheng. Such a wonderful, interesting talk today.
Yeah, thank you.
Thank you so much.
Yeah.
Right.
Thank you for joining today. And if you would like to join our future seminar, please don't forget to submission our email group. You can receive the latest seminar events and other very cool information and events held by the Optica U Tokyo. Thank you very much.